It is now time to use the Spark in order to analyze the P0 problem. And here is the rationale. We start with a given matrix A and suppose that somehow we manage to get its Spark being K. Turning now to the linear system AX equals B, suppose that we get two different solutions for it, x1 and x2. So both AX1 and AX2 equal B. Subtracting these two equations, we see that the non-zero vector x1 minus x2 must be in the null space of A. This immediately implies that the number of non-zeros in this vector is k and above. Our last step is to exploit the triangle inequality of the L0 norm that states that the number of non-zeros in x1 minus x2 is upper bounded by the sum of the number of non-zeros in x1 and x2. Look at this highlighted inequality. Does it remind you of something we have already seen? We got a new uncertainty rule that states that any two different solutions of AX equals B cannot be jointly sparse. Here is a theorem that states this clearly, and its proof is very simple, as we have just seen. Let's compare the two uncertainty laws we developed. In the 2-ortho case, the lower bound was 2 over the coherence. And in the new general setting, the lower bound is the Spark of A. Both these rules share the same structure, and both rely on basic properties of A. However, while coherence is easy to compute, Spark is impossible to get in general, and this gives a clear advantage to the 2-ortho result. On the other hand, the Spark is a stronger and more informative property than the coherence. In order to see that, notice that for an n by 2n 2-ortho case, the best bound would be twice the square root of n, whereas the Spark bound could be as high as n plus 1. As an immediate consequence of the uncertainty rule we have just developed, if a solution is found for AX equals B and it has less than half the Spark non-zeros, this implies that it must be the sparsest possible solution of this linear system. Put differently, if we find such a sparse enough solution, it is the globally optimal solution of the P0 problem. Observe that this is the same rationale as the one we have practiced in the 2-ortho case. We start from the uncertainty theorem that says that the number of non-zeros in x1 plus the number of non-zeros in x2 must be above the Spark of A. If we find a solution that has less than half the Spark non-zeros, this means that any other solution must be denser. And this implies that the solution we have found is the solution of P0, and it is unique. So to summarize, we are now able to put a simple condition for the uniqueness of the sparsest solution of a linear system AX equals B, and this applies to any matrix A. All that it takes is counting the number of non-zeros in the solution X and comparing this to half the Spark. On the downside, this result does not help in understanding what happens above the bound. Also, it does not say that such a sparse solution must exist. Lastly, since computing the Spark is virtually impossible, is this bound useful? So when it comes to the problem we have called P0, we are now slightly better equipped to answer some of the questions we have posed. More specifically, we can say that a sparse enough solution must be unique, and testing for this amounts to comparing the number of non-zeros in the solution to half the Spark. What about algorithms for finding such a solution? We will come to this in due time.